In the video lecture of Basic Circuit Element Inductor, we discussed that inductor stores energy in its magnetic field. Now, in this video lecture, we will be exploring that how an inductor stores energy in its magnetic field. So for that, let's consider a simple circuit in which we have a DC voltage source which is connected in series with a switch and an inductor. Now, initially when this switch is open, there is no current flowing in this circuit, so as a result, there is no voltage induced across the terminals of this inductor. So initially the current through this, let's say I initial, is equals to 0 ampere. Now at the instant when this switch is closed, so the current will start rising from its 0 values towards its maximum value. Let's say IM, and let's say the maximum value is I. Now during the time when the current is approaching from 0 to its maximum value, now we know that it is the properties of an inductor that it will always oppose the change in the current. Now according to Lenz's law, the inductor will always oppose the cause that produced it. So to oppose the original current in the circuit, the inductor must have stored energy in its magnetic field to overcome the original current or to oppose the original current in the circuit. So as a result, the voltage will be induced across the terminals of an inductor. Let's say V is the voltage which is induced across the terminals of this inductor. Now to find out how much energy will be stored by this inductor. So as we know that the voltage across an inductor is equals to LdI divided by dt. And we also know that the power is equals to the rate of energy. Now to find out the energy from this equation, let's multiply dt on both the sides, so we get the rate in energy is equals to P into dt. And we also know that the power is also equals to I into V. So instead of P we can write down du is equals to, instead of P we can write I into V dt. Now we also know that the voltage across an inductor is equals to LdI divided by 2 dt. So by putting the value of V in place of V here in this equation, so we get du is equals to I. Instead of V, we can write LdI divided by dt into dt. So dt will cancel dt, so we get du is equals to I L di. Now to remove this derivative, we can take integration on both the sides. So by taking integration on both the sides, so the integration will cancel the derivative, and the limits of this integration is from 0 to I. Because initially there is no current in the circuit, so as a result there is no voltage induced across the terminals of this inductor. Now when we close this switch, the current will start approaching to its maximum value from 0 towards I. So the energy will be equals to, L is constant in this case, which is the inductance of an inductor, from 0 to I into di. Now the integration of this term is equals to, U is equals to L, and the integration of this I di is I square divided by 2, and the limits are from 0 to I. So now putting these limits here, so we get L I square divided by 2. So the resulting energy which is stored by this inductor is equals to half Li square. So now this equation represents the amount of energy which is stored by this inductor, and this energy is released by the inductor when we open this switch. So as a result, an arc may happen on the terminals of this switch, and as a result the inductor will dissipate this energy rapidly, not instantaneously, when we open this switch. So it's all for today's presentation. If you have any doubt, ask in the comment section. See you in the next one.